Okay, so this is the lesson for equilibrium constants, and that you need to watch for homework. And let's go to the next slide. What I'm going to do with each of these slides is show you the slide for just a second. If you want to go to my website and print the slide out as I'm talking through it, go ahead and do that. Otherwise, I'm going to work the problems out. All right. So first of all, what is an equilibrium constant? Well, we've got our equation here, and this right here didn't load correct, so it should be a double arrow. It's a equilibrium equation, and we've got hydrogen plus iodide produces 2 hydroiodic acid, and the Kc, which is the equilibrium constant, so K is a constant, C is just used for the equilibrium. Doesn't matter too much. Anyhow, this right here, what you do is you take the products, okay, right here, and put those on top over the reactants. Put the reactants on the bottom. Divide it. Now, this right here, this 2, this should be squared. So it should look like this, Hi squared, just like we did with solubility constants, over H2I2. Okay, that right there is known as your equilibrium expression. Okay, it's always good PR, products over reactants. Okay, and that's always going to equal a value, which is the equilibrium constant. So this is always for when it's in equilibrium. Now let's get a few conceptual things down here. Let's say we increase Hi. So we increase Hi. It's going to shift to the left, and what's that going to do to the equilibrium constant? Well, the value is going to go up. If we increase either of the ones on the bottom, the equilibrium constant then is going to go down. Okay, so here's our first sample problem, and what I'm going to do is switch to the next slide and basically redo all this. But we have using this equilibrium expression here, and again that should have a double arrow though. Same thing, H2 plus I2 reacts to form 2Hi, hydroiodic acid. And so basically what we're going to have here is we're going to have some starting starting concentrations of the H and the I, and what we're going to decide then is what is the Kc, or the equilibrium constant, for this equation. Okay, so I'm going to switch to the next slide and it'll be blank, and we'll do this. Okay, so whenever you do an equilibrium problem, constant problem, you always want to make a chart. And what we're going to do is we're going to make the start, that's the starting concentration of each of the compounds, the change, okay, so how much they went up or down, so increased or decreased, and then the final, that's the final concentration once it reaches equilibrium. So let's start with the information we're given. We're given 1 mole of H2, and remember it's concentration, so that's molarity. We need to go moles per liter, and it says we put in a 5-liter vessel, so that means we start with 0.2 molar of H. Well, we have 1 mole of I2 also in 5 liters, so we also have 0.2 molar of I2. Okay, and then it says we start with 0 of Hi. Then the other bit of information we're given is a final concentration for I2, which is 0.0440. Now, every time we use an I2, we have to use an H2. Because where do these two go? Well, they go to make Hi. You can't make Hi with just I2 or with just H2. You need both of them. So the final concentration of H2 is also going to be 0.044. Okay, and so now we can find the change. 0.2 subtract 0.044 gives us negative. I put a negative sign there, and that's indicating that we're losing, or we're using some of that. 0.156, and same thing, we're using up some of that I2 as well. So 0.2 subtract 0.044 gives us negative 0.152. And again, we're using it up. Okay, the equilibrium shifting, the whole thing shifting to the right. Okay. Okay, so the next step is we need to think about this conceptually. Again, whenever you use an H2, you use an I2. Okay, so ready? One of these and one of these will produce two HIs. Okay, so if we know the concentration, the changing concentration of H, we know that HI is twice that. Same thing, if we know the ending concentration of I2, we know that HI is going to be double that. Okay, so now we know our final concentration. It's just double the concentration of this. Okay, so then our final concentration is that. Alright, so now what we've got is we've got all the concentrations at equilibrium of each of the species. So what we're going to do is we're going to go ahead and plug it into our equilibrium expression. Okay, equilibrium expression is always products over reactants. Okay, so products over reactants. So we want to go 0.13 0.312, and remember we want to square it because it has a coefficient of 2, over 0.044 times 0.044. Okay, so this one times this one, or we can simplify it and square it, and that's going to equal our Kc. That'll give us a final value of 50.3. Okay, we're done with that problem. Alright, on to problem number 2. Okay, so in the previous problem we were asked to find the equilibrium constant if given the concentrations, starting concentrations of each of the compounds. In this problem we're going to do just the opposite. We're going to be given the equilibrium constant, which we solved in the last problem, and remember it's unique to each reaction. And we're going to be given the constant, and we're going to try to find the final concentrations of each of the compounds. So the formatting, as you can see, obviously didn't transfer over too well, but like I said, you can go on the website, print off this this slide, but I'm going to do it on the next slide. Okay, so in this problem we're given a starting concentration of each of these, and don't forget it's already given in molarity, but oh shoot. 0.0, 0.01, 0.01, and 0.02 molar. Okay, so that's given in the problem. And then it says, finally, what are the concentrations of each of these at equilibrium? So we want to find the final concentrations, okay, which is at equilibrium. Okay, so the next step is trying to find out which way the equilibrium shifts. Well, first of all, is it in equilibrium? Okay. If it is, then we should be able to plug it into our equilibrium expression, and it should equal what? Well, the constant, 50.3. So let's try it. All right, products over reactants, 0.02 squared. Okay, because there's a 2 up there, so we got to square it. If there's a 3, we'd put it to the third power. Over 0.01 times 0.01, or 0.01. We just simplify it, 0.01 squared. That equals 4. Okay, so it's not at equilibrium to start with. If it was, this number would be 50.3. So what we need to decide is which way is it going to shift. So this number needs to become larger. So what we need to do, we need to make the top number increase. If we increase this top number, this top concentration, which is the products, then it's going to make this increase. And at the same time, invariably, so we need to make that one increase. At the same time, what's going to happen is that one's going to decrease. So which way is it going to shift? It's going to shift to the right because we want the products to increase. So it's going to shift this way. If this number was greater than 50.3, it would obviously shift to the left because we need to make it smaller. Or in other words, we need to increase the reactants. Okay, so we'll continue now in filling out our table. All right, so we need to know the change. Well, we don't know how much it changes, but we know that since it's going to shift to the right, we're going to use up the reactants. So that means we're going to use up some of this 0.01. Okay, so I put the negative x. We don't know how much though, so we're just going to say x. Whatever we use of H2, we're going to use the exact same amount of I2 because they have to come together, 1 for 1, to make 2 of those. And then this is going to increase, okay, because we said it's going to shift to the right. By how much? Well, if this one decreases by x, this one increases by 2x, because for every one of these, we produce 2 of those. Okay, so our values are going to be 0.01 minus x, and this is going to be 0.02 plus 2x. Okay, so let's go ahead and plug it into our equilibrium expression. Equals HI squared over I2 square I2 and H2. Alright, so we're going to plug in each of these values into here. Okay, so on the top we're going to be 0.02 plus 2x, and that's going to be squared over 0.01 minus x and times 0.01 minus x, or just that squared. And that equals our equilibrium constant, which is 50.3 we were given in the beginning of the problem. Okay, so now what we need to do, we need to solve for x. Once we find x, we can plug it back into our final values here. Plug them back into our final values, and we can solve for all those concentrations. So that's what we're going to be doing. Okay, so let's take the square root of everything. Okay, so if we take the square root of everything, it will give us my equation right over here. And now we need to multiply both sides by 0.01 minus x. Okay, so multiply both sides by 0.01 minus x. Top and bottom will cancel out. Distribute the 7.1 in there. So it's going to end up with... Okay, so then next we need to combine like terms, so add 7.1x to both sides. So that'll give us 9.1x on this side, which I'm not showing, and then subtract 0.02 from both sides, and that'll give us 0.051. So that means x is going to be 5.6 times 10 to the negative third. Okay, so now what we're going to need to do is we're going to need to plug this in for each of these, our starting values. And that'll give us our final concentrations, which I'll do on the next slide. Okay, concentration of H2 is the same as I2. And if that is 0.01 minus x. If we substitute our value 5.6 times 10 to the negative third for x, that gives us 0.0044 molar. So that's the concentration of H2 and I2. HI's concentration, we need to substitute x in for this expression, which represents our final equilibrium concentration. That gives 0.031 molar. All right, so there's H2 and I2, and there is HI. Okay, that's it with the equilibrium expression. I know you're disappointed as much as I am, but anyways, tomorrow we'll work on these problems in class.